Hello, today we're going to be talking about moles and molar mass. The mole is a unit in chemistry that is very important for counting particles. It's kind of like a dozen. So we know that 1 dozen things is the same as saying 12 things or 12 items, right? So in chemistry, the atoms, particles, ions, whatever it is we're counting, they're so small that even using something like a dozen is impractical. So instead we use the mole. 1 mole is equal to 6.022 times 10 to the 23rd items, or particles in this case. So that number is huge. Imagine, moving the decimal over until you get 23 places further down. It's a gigantic number, and we call that Avogadro's number. But we can manipulate it kind of the same way we do with a dozen. So if I have 2 dozen items, we know that that is 24. And if we have 2 moles, we know that that would be 12.044 times 10 to the 23rd. And of course, you would rewrite that into scientific notation, 1.2044 times 10 to the 24th. You could also go the other way around. So if I have a half dozen, we know that that's 6 items. So you can have 1/2 of a mole, and that would be 3.011 times 10 to the 23rd items. So a mole is just a way that we count things. It's just, it happens to be this huge number because atoms, molecules, ions, electrons, whatever it is we're counting is very tiny. Now on the periodic table, they give a couple things in each box for the elements. So let's look at nitrogen, for example. Nitrogen will give you, 7, and that's the number of protons, but it will also give you a number like 14.0067. This is the weighted average mass of the isotopes that are naturally occurring on Earth for nitrogen. So it's like an average mass, right? Typically this is given in AMU, which is atomic mass unit. But what's great about this is that it also tells you the mass in grams if you had 1 mole of nitrogen. So if you took 6.022 times 10 to the 23rd atoms of nitrogen and put it on a scale, it would weigh 14.0067 grams, assuming it was a representative sample. Now let's look at another example. Let's look at like oxygen. Oxygen has a different mass. Oxygen's mass is 15.9994, and we'll have 8 protons. But that means if you took 6.022 times 10 to the 23rd atoms of oxygen and put it on a scale, it would weigh close to 16 grams. So each of the elements has its own molar mass, is what we call it, molar mass, so it's the same number in AMU or in grams. You can also calculate the molar mass for a compound. So let's say I want to find the molar mass for NO2, nitrogen dioxide. So in that compound, there's 1 nitrogen and 2 oxygens. What you can do is you multiply by the mass from the periodic table, so the mass of NO2 from just nitrogen would be the same, 14.0067, and the mass from the 2 oxygen atoms would be 31.9988. And to find the total mass, you would just add those 2 together, and you get 46.0055. Now, normally we don't use that many significant digits. You'll typically be using 3 or 4 significant figures instead of 6, but this is just for illustration purposes. And your unit here, you would either be using AMU, but more common, we're going to be measuring in grams because that's something that we can measure on a scale. So it would be grams per mole. And again, so that is if you had 6.022 times 10 to the 23rd molecules of NO2 would weigh 46.0055 grams. This is probably the most frequent calculation we do in chemistry class is molar mass, so it becomes very important that you're able to do these quickly and accurately. So we can use molar mass and Avogadro's number to convert between quantities in chemistry. We call those mole conversions. So if mass is typically in grams, and then we have moles for counting, and then we have like the number of particles, which is Avogadro's number. So it's the number of particles. Those are our three big units that we're going to be talking about. Mass in grams, moles, and then number of particles. Remember, particles can be lots of different things. They could be molecules, they could be atoms, formula units, ions, electrons, any type of individual discrete unit of things could be a particle. So your kind of strategy with mole conversions is looking at if you have mass, you can get from mass, that's a weird arrow, mass to moles using the molar mass, which is in grams per mole. Notice how both of those units, grams and moles, are in the molar mass. Once you have moles, you can get to the number of particles using Avogadro's number, which is 6.022 times 10 to the 23rd, and that's the number of things, I'm just going to use number of things per mole. Notice how number of particles and moles are both there. So that's kind of our strategy. We can't jump directly from mass to number. We have to change it to moles first and then to number of particles. Or if we have the number of particles, we can go to moles and back to mass from there. And of course, you can do just this part if you want to, just this part if you need to, or the whole thing, depending on what the question's asking. Okay, let's look at a couple of examples. Let's say, for example, you have a 15.0 gram sample of lead 2 chloride, PbCl2. So the first thing you want to do is you need the molar mass of PbCl2. So we need to find the mass on the periodic table. For lead, that's 207.2, and for chlorine, that's 35.5. Now, in our compound, there's one lead and two chlorines, so 207.2. For chlorine, that would be 71, and then you add up to find the total mass, or 278.2. Now that you have the molar mass, we can use that in our equation here, and we can convert those grams to moles. So 278.2 grams per mole for the lead 2 chloride. And by putting the grams on the bottom, you can cancel out grams. And then you divide. So 15 times 1 over 278 is the same thing as saying 15 divided by 278.2. And so when you calculate that, you get 0.0539 moles of the PbCl2. I'm using 3 significant digits here. The zeros at the front don't count, and I'm using those 3 because there's 3 in my original measurement. Now that we have moles, you can, just use those moles if that's what you're looking for, or you can convert that into atoms or molecules. So let's go ahead and find out how many atoms of lead are in the sample. 0.0539 moles. So moles of the lead chloride. Now, in each molecule of the lead 2 chloride, there is 1 atom of lead. Because I just want to look at the lead. And then, since I want atoms, I need to use Avogadro's number, 6.022 times 10 to the 23rd atoms, or whatever type of particle, per mole, and now moles will cancel. So when you multiply that out, and again, we're using those 3 significant figures, 3.25 times 10 to the 22nd atoms of lead. Now we can do the same thing for the chlorine. If we want to find just the atoms of chlorine that are in that 15 gram sample, we can take the moles of the lead 2 chloride, but this time there are 2 chlorine atoms for every 1 PbCl2. And we would still use Avogadro's number, because that's always the same. That's how many atoms are in 1 mole. Moles cancel, the lead 2 chloride cancels. And so this time you do 0.0539 times 2 times Avogadro's number. And you would get the 6.49 times 10 to the 22nd atoms of chlorine. Or, because we already changed it into atoms, we can just multiply directly by 2 to get the atoms of chlorine. But I wanted to show you both ways. A couple things to remember here is you always show your work every single time. You always show your work. That is a requirement for the AP exam. You should always factor label, which is another way of saying you cancel your units. It helps you keep track of where you are in your problem. And you should always round to the correct number of significant figures. However many sig figs are in your original measurement, that's how many sig figs should be in your answer. And then conversion factors, which are like the molar mass and Avogadro's number. So things that you're using to convert don't affect your significant digits. Yeah. Let's do one more example. Let's say, for example, we have 0.490 grams of calcium carbonate. And I want to know how many formula units of calcium carbonate are in that 0.49 gram sample. Remember, a formula unit is another way of saying how many compounds. We're going to talk about that more when we get to ionic versus covalent compounds later in the year. But for now, they're just different types of particles. So how many formula units? So our first step is to always find the molar mass. Calcium, there's one of those in the compound. Carbon, there's 1, and oxygen, there's 3. Calcium's mass from the periodic table is 40.1, carbon's is 12, oxygen's is 16, and remember I'm rounding a little bit. So 40.1, 12.0, and 48, and then you add it together to get the overall molar mass, grams per mole. Now from there, we can change grams to moles. 0.490 grams of calcium carbonate. We can use the 100.1 grams on the bottom, that way grams cancel. And so if you stop there, you would have moles of calcium carbonate. But I don't want moles, I want formula units, or particles. So I can use Avogadro's number to get the number of formula units. I'm going to abbreviate a little bit. That's how many formula units are in 1 mole. Moles cancel. So you would do 0.490 divided by 100.1 times Avogadro's number, and we're using 3 sig figs based on our original measurement, so we get 2.95 times 10 to the 21st formula units of the calcium carbonate. Now remember, your final answer should have the same sig figs as your original measurement, and the zeros at the end count when there's a decimal place. You also need to make sure you label with the unit and the substance. And show your work.